Section 7.3, Logarithmic Functions as Inverses. So today, students are going to be able to write logarithmic functions, evaluate logarithmic functions, and graph them. A logarithm is just the inverse of your exponential function. So an exponential function could look like this. Okay, it has an exponent, just like you were used to having, and I call this our friend Ben. Okay, b is little because it's the base. E is the exponent. And n is the number that it equals. Okay, so for instance, 2 to the third power equals 8. 2 is the base, 3 is the exponent, and 8 is the number that it actually equals. So we can convert our exponential function into a logarithmic function, and all what you do is rewrite it. So we write the log base b of n equals e. So the reason I have b as a lowercase letter is because it's a small subscript over here, okay? And then your number comes next, and then e. So a bunch of people struggle with writing this. It's like this is all on one line, all the same. B is the subscript that is below it, okay? And I just remember this as Benny, our friend Benny, that's his nickname for Ben, okay, and you just write the word log in front of it. It's the way I remember the order to rewrite my letters in, okay? So if we were using the example of 2 to the third equals 8, we would write this as the log base 2 of 8 equals 3. Because 2 was your base, 3 was your exponent, and 8 was your number. So let's learn how to write exponential equations in logarithmic form. So I gave you 36 equals 6 to the second power. So I need to determine what the base is. And if you don't know what the base is, obviously look for the exponent, and the number that has the exponent is your base. So 6 is my base, 2 is my exponent, which makes 36 my number. So if we rewrite it in logarithmic form, we write the log base 6 of 36 equals 2, because remember we write the log and then we write b in e. Our second example has 2/3 to the third power equals 8/27. So it doesn't matter that we have fractions in this time. So 2/3 is my base because it has 3 as the exponent, which makes 8/27 my number. So we write the log base 2/3 of 8/27 equals 3. Our last example converting to logarithmic form is 1 equals 3 to the 0 power. 3 is my base because 0 is its exponent and 1 is the number. So we write the log base 3 of 1 equals 0. Now we're going to look at evaluating a logarithm. So in example 4, they have the log base 5 of 125. And you should be used to seeing it with an equal sign and then something else on the other side of the equal sign. So for all of these problems, we are going to add equals x. Again, it's not given to you, we're going to add it. Okay, so that makes 5 my base, 125, my number, and then x as my exponent. Okay, let's rewrite it in Ben form. So we write 5 to the x power equals 125. So now, think 5 to what power gives me 125? 5 to the third power. And then when the bases are the same, you find out that you get 3 as your answer. Example 5, we have the log base 4 of 32. Again, we're still evaluating it, so since it's missing the equal sign in the other number, we're going to write equals x. So 4 is my base, 32 is my number, x is my exponent. So rewrite it in exponential form, in bin form. So we have 4 to the x power equals 32. So now if you think, 4 to what power gives me 32? So 4 to the second power gives me 16, but 4 to the third power gives me 64. There's no way 4 to any power would give me 32, so we have to change both of our bases. So since we have the number 4, I know that we could rewrite 4 as 2 to the second power, because 2 to the second power is 4. So now let's see, is 2 to a power 32 as well? So 2 to the fifth power is 32. So up here we need to multiply our exponents. So we get 2 to the 2x power equals 2 to the fifth. When the bases are the same, they cancel out, and we get 2x equals 5. Divide by 2, and our answer is x equals 5/2. Example 6, we have the log base 64 of 132. So we're going to add our equal sign and our x. 64 is our base, 132 is our number, x is our exponent. So we write 64 to the x power equals 1 over 32. Okay, whenever you see a fraction, you know that to get from a whole number to a fraction, your exponent has to be negative. So I hope you also know that 64 to some power is never going to give you a base of 32. So we need to find a number that will give us both 64 and will give us 32. So I might start by thinking about the base of 4, because earlier I found that 4 to the third power was 64. However, 4 to the second power gives me 16, not 32, so we need to pick a value that's less than 4. So let's work with 2 maybe. 2 to the fifth power is 32, and 2 to the sixth power is 64, so that works. So let's go ahead and start to rewrite it. So 64 is 2 to the sixth power, and 32 is 2 to the fifth power. Now, I cannot cancel out when I have a fraction, so to make this 2 to the fifth power come to the numerator, remember just like I said, it's going to change it, and it's going to make it negative. When you multiply 6 and x together, that's going to make this go away, and you just have 6x. Since the bases are the same now, the bases can cancel out, and you get 6x equals negative 5. Divide by 6, and your answer is negative 5/6. A common logarithm is a logarithm that has a base of 10. So if I were to write this, the log base 10 of 100 equals 2. So since this log has a base of 10, we call it the common logarithm. In your book, you will never see the 10 written. It will just look like this. The log of 100 equals 2. So when there is no base down here, it's an invisible 10 because it's assumed that you know that it's a common logarithm. Now we're going to move on into graphing logarithmic functions. So the general form is y equals a times the log base b of x minus h plus k. Just like normal, a is going to vertically stretch it, vertically compress it, or reflect it across our x-axis. The x minus h is going to either move it to the left or it's going to move it to the right. The plus k at the end is going to move it up or it's going to move it down. Okay, for your 2 points that you are always going to graph, it's going to be the point 1, 0, and then you're going to take whatever the base is and the base comma 1 is going to be your second point. Logarithmic graphs are just the inverse of an exponential graph. So let's say our exponential graph looks like this. The inverse of it, remember, it reflects it over this invisible y equals x line. So logarithmic graphs look like this. So our logarithmic graphs have an asymptote. Instead of it being y equals, it starts at x equals 0, and then depending on the shifts, it could move. So it's only the left and the right shifts that's going to affect this. Instead of having a y-intercept, you now have an x-intercept. You could have both, but you normally only have an x-intercept. The domain is no longer negative infinity to positive infinity, but instead the range is now negative infinity to positive infinity. The domain is based on what h is, so it's normally h to infinity, and it can't become h because of the asymptote. And then we're also going to look at the end behavior, but it's going to be a little different because I won't be able to go past this asymptote that's right here. We're going to do this last example that has everything in it all at one time. So we have y equals 2 times the log base 3 of x minus 4 plus 5. So the 2 is going to vertically stretch our points. The 4 is going to move it to the right 4, and the plus 5 is going to move it up 5. Okay, so we start always with the point 1, 0, and then base, comma, 1. What is our base in this logarithmic form? So 3 is our base, so we are instead going to graph the point 3, 1. Okay, so then we always start by vertically stretching it. So we take our y values and we multiply them by 2. So 0 times 2 keeps it 0. 1 times 2 gives me 2. So those are the 2 points I'm going to start with. 1, 0, and 3, 2. Okay, this is what logarithmic graphs look like. They're exponential functions on their sides. Remember, because the logarithmic form is the inverse of your exponential form. So now I take these 2 points and I move them to the right 4, and I go up 5. So 1, 2, 3, 4. 1, 2, 3, 4, 5. So then I move my other point to the right 1, 2, 3, 4. 1, 2, 3, 4, 5. Okay, before, you didn't know it, but since our asymptote for the exponential functions was at y equals 0, now your asymptote is at x equals 0. So since this minus 4 is going to move it to the right 4, it's going to move my asymptote to the right 1, 2, 3, 4, and I'm going to have an invisible vertical line right here at 4. Okay, so my graph can never go through my vertical line. It should look something like this. So now I'm going to state our characteristics. So our first characteristic is our asymptote, and the asymptote is now x equals 4 because remember it's a vertical line. And it shifted to positive 4 because we moved our points to the right 4. Now let's find the x-intercept. So to find our x-intercept, you plug in 0 for y. So we have 0 equals the log base 3 of x minus 4 plus 5. And we're trying to solve for this x that's in here. So to move our positive 5 to the other side, we subtract it. Since the x is in the parentheses, we need to change it to our exponential form. So this is our base, our number, our exponent. So we do 3 to the negative 5th power equals x minus 4. The negative moves it to the denominator and makes it positive, so it's 1 over 243. And then to move the minus 4 to the other side, we add 4. You will have to multiply that 4 by 243 over 243, and that's going to give us an X-intercept of 973 over 243, comma, 0, because remember, it's an X-intercept. This makes sense if we look at our graph because 973 over 243 is just a little before the number 4, okay? And remember, 4 is our asymptote. So since 4 is our asymptote, that affects our domain. So it's now 4 to infinity because it cannot be the number 4. And the range has now swapped, and so it's now negative infinity to positive infinity for your range. Now let's talk about the end behavior. So we cannot go to negative infinity because we can't get past our asymptote. So as x goes to 4, f of x is going to, and since our graph is going down, it's going towards negative infinity. And then x can go to positive infinity. F of x is also going to positive infinity.